So this question asks, use the energy values for food, here's our food, in the table above, this would be the table that we have, determine each of the following. So we're either going to determine this in kilojoules, kilocalories, or in one of the instances it's actually going to be grams. But the kilocalorie is the exact same as a food calorie, all right? And the first question asks the total kilojoules of 2 tablespoons of crunchy peanut butter that contains 6 grams of carbohydrates. So we have 6 grams of carbs, all right? 9 grams of fat, 6 grams of carbs, 16 grams of fat, and 7 grams of protein. So we're going to start with the 6 grams of carbs, and we know that, so we're trying to look for the kilojoules, so we're going to be in this column right here. And so we know that there's going to be 17 kilojoules for every gram of carbs. Plus, the next one asks for 16 grams of fat. So we have 16 grams of fat. All right, so fat is going to be 38 kilojoules per gram of fat. All right, plus, then we have 7 grams of protein. So 7 grams of protein. Grams of protein is going to be now 17 kilojoules per gram of protein. So grams of protein cancel, grams of fats cancel, grams of carbohydrates cancel. Take 6 times 17 plus 16 times 38 plus 7 times 17, and that's going to give us a grand total of 829 kilojoules of energy, which will be in that 2 tablespoons of crunchy peanut butter. All right. Now the next one is just going to be a little bit more difficult. In that one, we're going to be looking for the grams of protein in soup. So it's going to require just a tad bit of algebra. I will show you how to work through that problem, how to manipulate the algebra. But it's probably the hardest problem in the set. All right, but we'll get through it. It's not too bad. All right, so we'll erase that. Got that all nice and clean. So now this question asks us the grams of protein in 1 cup of soup that has 110 kilocalories with 9 grams of carbohydrates and 6 grams of fat. So the total amount of energy is going to be equal to 110 kilocalories. And what we're looking for is the grams of protein. So we're going to start with what's given to us. We have 9 grams of carbohydrates. So we have 9 grams of carbs. All right. Oops, I'm going to move that over just a hair so I have extra room. All right. So we're going to have 9 grams of carbs. All right. Now this gives us information on the kilocalories, so we'll be working with this column. So we know that the grams of carbs, there is going to be 4 kilocalories per gram of carb. Okay. Plus, he gives us 6 grams of fat. So this is going to be 6 grams of fat. We go to the fat and we see that there's going to be 9 kilocalories per gram of fat. Plus, now is where we have to use a little bit of algebra. It has protein. So we have X grams of protein times, this is going to be 4 kilocalories per gram of protein. And this is all equal to 110 kilocalories. All right. Now, if we go through here, what we get is we multiply this, the grams of carbs cancel, so we get 36 kilocalories plus 6 times 9 is going to be 54 kilocalories. Once again, the grams of fat cancel. Plus, this now becomes 4x is equal to 110 kilocalories. Now we got to get the 4x by itself, so 4x is going to be equal to, this is going to be equal to 90. So you take 110 minus 90, that's going to give us 20, right? So that's going to be 20. And if we solve for x, we're going to have to divide this by 4, all right? Our x is going to be equal to 5. Now, the units here are going to be then grams of protein. So in this cup of soup is going to be 5 grams of protein. See, I told you it's a little bit more difficult because of the algebra you have to apply to this. But it isn't too bad. Once you write everything out, keep track of your units, you should be just fine. It's not too bad at all. Just got a few more to do. But it's amazing how much energy there is in just a cup of soup. That seems quite a bit, but probably healthy soup. All right, we'll get that erased. All right. The next problem states the kilocalories in 1 can of cola that has 40 grams of carbohydrates, no fats or proteins. So we have 40 grams of carbs, all right, and we want to know the kilocalories. So we're going to look at the kilocalories, all right. If we have 40 grams of carbs, all right, and the carbs is going to have an energy value of 4 kilocalories per gram, the grams will cancel, and we have 4 times 40, which is going to give us 160 kilocalories in this problem. All right, quite a bit of calories just for a can of soda, but it's all right. Must not be diet. Who knows? All right. The last one here is going to be the total kilocalories for a diet that consists of 68 grams of carbohydrates. So we have 68 grams of carbs, all right, 9 grams of fat, 150 grams of protein. So this must be a complete total diet. And we were looking at the total kilocalories. So we're working with this total kilocalories. So we have the carbs. And so this would be 4 kilocalories per gram of carb, plus next will be 9 grams of fat. So we have 9 grams of fat. So we look at the 9 grams of fat, and that's going to be 9 kilocalories per gram of fat, plus here we have 150 grams of protein. So 150 grams of protein, we look at the protein, and that's going to be 4 kilocalories per gram of protein. So the grams of protein cancel, grams of fat cancel, and the grams of carbohydrates cancel. So simply do some arithmetic. We'll take the 68 times 4 plus 9 times 9 plus 150 times 4. You go through and you do this arithmetic real quick. You get 953 kilocalories per mole. All right. Now, this is a nice simple problem. It's not too bad. Next, what we're going to be working with is we're going to be working with temperature. Now, remember, temperature is not the same as heat or energy. All right? Temperature actually is the measure of the average kinetic energy of the molecules that make up that substance. So that's actually what the temperature is. It's not energy. It's the average kinetic energy of the molecule. So basically the movement, how fast are those molecules moving, is what temperature is going to be equal to. Now there are 3 different types of temperature scales that we talk about. There's going to be the degrees Fahrenheit, which we are most familiar with living here in America. There's going to be the Celsius scale, which is most familiar to those people living throughout the world. And then lastly, there's what's the Kelvin scale, and that's used most primarily for scientists. Okay. So I'm going to write a couple of the equations up here on top. And so the temperature of degrees Fahrenheit, if we're going to do some conversions, is going to be equal to 1.8 times the temperature in degrees Celsius plus 32. Now we can work this backwards and we can find, the temperature in degrees Celsius is going to be equal to the temperature in degrees Fahrenheit minus 32 divided by 1.8. All right. So that's the conversion from the temperature degree Fahrenheit if we're given the temperature degree Celsius. If we're given the temperature degree Fahrenheit, we need to calculate temperature degree Celsius. This is the equation we're going to use. Lastly, the Kelvin scale. The temperature in the Kelvin scale is equal to the temperature in degrees Celsius plus 273. This is sometimes referred to as the absolute temperature scale. So I'm just going to leave them up there for you. And so what we want to do for this problem is we want to solve the following temperature conversions. So we're going to take 25 degrees Celsius and we're going to convert that into degrees Fahrenheit. So since we want to use this scale here because we're given we want to use this equation here because we're given the temperature in degrees Celsius, we want to solve for the temperature in degrees Fahrenheit. So the temperature of the degrees Fahrenheit is going to be equal to 1.8 times the temperature in degrees Celsius, which is going to be 25 degrees Celsius, plus 32. You go through and you do this basic arithmetic, and you will end up getting 77 degrees Fahrenheit, all right, for degrees Fahrenheit. Not too bad, all right, pretty simple. Actually, none of these are all that bad. They're pretty basic. We're just got to figure out which equation we want to use, and then we'll just simply plug into that equation. All right, we use yellow. We haven't used that in a while. So in this case, what we want to do is we're going to go from 65.3 degrees Fahrenheit, and we're going to convert that into degrees Celsius. So we're given the temperature degrees Fahrenheit. We want to solve for temperature in degrees Celsius. And so this is going to be temperature in degrees Celsius is going to be equal to 65.3 minus 32 divided by 1.8. We go through and do this arithmetic and we end up with 18.5 degrees Celsius. Kind of misleading. You think of 18.5 degrees Celsius, 18.5 degrees, whoa, that's kind of a cold temperature, but not in the degrees Celsius. It's actually 65.3 degrees Fahrenheit. And that, wow, as far as I'm concerned, that's a pretty comfortable temperature. Not too bad. All right, the next one is going to be minus 27 degrees Celsius, and we want to convert that into degrees Kelvin. For that, we're going to be using this temperature, or this equation right here. So the temperature in Kelvin is going to be equal to the temperature in degrees Celsius, so that's a minus 27 plus 273. We go through and do that arithmetic, and that's going to be 246 Kelvin. Excuse me. We're not real familiar with this temperature scale of kelvins. It's not used a whole lot outside the scientific community. It's all based off of what's called the absolute zero, and that's a temperature scale, or that's a temperature in which basically all matter stops moving. That includes the electrons. We actually can't get to that temperature scale, absolute zero. We can get extremely close to it, but we can't actually get to the temperature scale of 0 Kelvin. And that's a whole other issue, much longer time, much more, a harder discussion than I care to do at this time of the night. All right. Part D is we're going to take 62 degrees Celsius, and we're going to convert that yet once again into Kelvin. All right. We're going to use this equation here. So the temperature Kelvin is going to be equal to the temperature in degrees Celsius, which is going to be 62 degrees Celsius plus 273. We add those two numbers up, we get 335 Kelvin. All right. And then the last problem for this, or the last portion for this problem, is going to be, we're going to be converting from Fahrenheit to degrees Celsius. All right. All right, Fahrenheit to degrees Celsius. So here we're going to take 114 degrees Fahrenheit, and we're going to convert that into degrees Celsius. So we're given the temperature in Fahrenheit, and we need to convert that into Celsius. And so our temperature in Celsius is going to be equal to 114 minus 32 divided by 1.8. We go through and do that arithmetic real quick, and we're going to get 45.56 degrees Celsius. So sort of a pretty warm day, at least where I'm from. Maybe in Arizona, that's probably a typical summer day. I do not know. All right. So now we've done those temperatures, we still have a few more problems, or at least one more problem we're going to be doing that deals with energy. All right? That deals with energy. And this is going to be having to deal with some phase conversions. Most of these are going to be condensing or vaporization. All right. So in order for those, I have to give you some values. All right. A lot of values in this chapter here. And so for those, I'm going to give you the heat of vaporization. So heat of vaporization. So I have to look these up. I don't expect you to memorize these. But 1 gram of water, to vaporize 1 gram of water, we have to put into the system 540 calories. Right? Or this is going to be equal to 2,260 joules. All right? So that's information that's going to be given to you. You would actually end up looking that up in a book. So what we want to look at, what we're trying to calculate, the calories to condense. Right? So if we want to condense, that means going from gas to liquid of 100 grams of steam. So we're going to start with 100 grams of steam. That's just water vapor. So we have 100 grams of steam. And we were looking for the calories, so we'll be using this number right here. And there's going to be 540 calories per 1 gram. All right. So we do the arithmetic here. This is going to be 5,400 calories, and that's going to be released. So that's the amount of energy that's going to be released by that. All right. So if we're going to condense 10 grams of steam from vapor to liquid, that system is going to release 540 calories will be released into the atmosphere, into the surroundings. All right. So if you're going from a vapor phase to a liquid phase, that means that the vapor had to release that amount of energy in order for it to be going into the liquid phase. So go from a vapor phase to a liquid phase, the system has to give up energy. If it's going from a liquid phase to a gas state phase or a vapor phase, it has to absorb that amount it has to absorb energy. So here we're going to be calculating the joules to condense 7.6 grams of steam. So we have 7.60 grams of steam that's given to us. Once again, we're looking at joules. And so this is going to be condensing once again. So it's going to go from a vapor to a liquid. And since we're dealing with joules, this is going to be 2,260 joules in 1 gram. So we go through and do the arithmetic for this. This becomes 17,176. Yep, 76. And so that's going to be joules, and that once again is going to be released because we're going from a vapor phase into a liquid phase. So it's condensing. All right. If you're looking at positive or negatives, that would be a negative 17,000 because that means that the system is losing that amount of energy. But the book isn't too worried about positive or negative. They just want you as a student to understand whether it's absorbed or released. All right. Now for this portion of the problem, what we need to do is we need to determine the kilocalories to vaporize 44 grams of water. So we start with the 44 grams of water, all right? Now it's asking for kilocalories, but what's given to us is going to be calories. So we could divide this by 1,000 or move the decimal point 3 places to the left, and so this becomes equal to 0.54 kilocalories for 1 gram of water. So we'll just simply use that conversion, and for our 1 gram of water, there's going to be 0.54 kilocalories. We go through and do this arithmetic, we get 23.76 kilocalories. Now, since it's going from, we have to vaporize the water, so going from liquid water to gaseous water, that's going to be heat that's going to be absorbed by the system, or it will be positive. All right? And we have just one more of these problems. Oops, we're going to go to blue here. Try blue. You didn't have to necessarily convert it here. You could have converted it to the end. So you got 23,760 and just convert that, divide that by 1,000. You'd have gotten 23.76, which is what we got. So it doesn't matter where you do the conversion, whether you do it sort of in the middle there or you want to do it towards the end. It's okay. It doesn't matter as long as it gets done, right? So in this portion, what we want to do is we're going to be looking at the kilojoules to vaporize 5 kilograms of water. So we're starting out with 5 kilograms of water. Now the interesting thing with this problem is that we're given it in 1 gram of water. So we need to convert this into kilograms. So if we're going to convert this into kilograms, we know that for every 1 kilogram, that's equal to 1,000 grams. Now you can either do it this way, or you can simply just move the decimal point 3 places to the right. And we need to vaporize this, and we're looking at kilojoules. Once again, we are given 2,260 2,260 joules. We need to convert that into kilojoules, so that becomes equal to 2.26 kilojoules. So we could just simply do that arithmetic. And so we end up getting, for every 1 gram of water, the grams are going to cancel. This requires 2.26 kilojoules. All right, we go through, we see that the grams cancel, the kilograms cancel. We go through and do this arithmetic, and what we end up getting is we get 11,300 kilojoules. And once again, this is going to be vaporizing, so that means that the water has to absorb this amount of heat, so this would be absorbed. Okay. Thus ends the problems for this chapter. If you happen to have any questions, please let me know.